Hello, in this class we are going to look at batteries. Basically, they are devices that are very ubiquitous, they are all over the place, and at any given point in time, all of us seem to be using batteries. So, in this class we will look at some of the basic concepts associated with batteries, the science of the batteries and how it functions and so on. In fact, I do not know if you realize that, but in any given social setting that you may be in, chances are there are more batteries than there are people. You will typically find this to be true because at any point in time most of us seem to be carrying our mobile phone with us. We also typically have a wristwatch of some kind that we are wearing. So, right there are 2 batteries. So, already if you see 10 people there are 20 batteries there. So, that is the extent to which this technology is now commonplace in our life. We do not even realize it, we do not realize that we are carrying batteries. On top of it, if you have a laptop or a computer that has a battery, and if you have a calculator, your scientific calculator, whatever you are carrying has a battery. So, lots of things have batteries which we do not even realize that it is having a battery, and over and above this we carry a power bank or something to extend the range of our mobile phone. So, that is only a battery more or less. So, this kind of situation exists. So, therefore, it is a technology that is interesting to look at. In the context of non-conventional sources of energy, batteries play a very critical role, very important role, because a lot of those technologies, we spoke about solar energy, we spoke about wind energy, we spoke a lot of detail about how those technologies function. But one common aspect with all of those technologies is that they do not produce power in a consistent way throughout the day and throughout the year. So, there is significant impact of the time of the day on the power being produced, the conditions at the time of day determining the power being produced. If it is solar technology, it could be just passing cloud could make a difference, rain could make a difference, or a completely cloudy day could make a difference, and of course, there is a big huge difference between day and night. So, that difference is there. If it is wind technology, again you may have a gust of wind, you may have steady wind flowing, you may have fast wind going. So, again as the day progresses, you may have different conditions for power generation, and then also there are seasonal variations. So, all of these impact those 2 major technologies that are being pursued actively around the world. So, you also always need to have some energy storage process or technology to go along with these non-conventional sources of energy to really utilize that non-conventional source of energy, and that is the context in which we will study let us say batteries, and later we will look at fuel cells. Both of these are they are not, fuel cell is not storing energy, but they give you the flexibility of distributing the power that you generate across the day. So, you generate power, so you may at times be generating more power than you need. So, you need a way in which you can, but your utility, so your utility pattern has a different profile. It does not necessarily match with the profile of the power that you are generating. So, for example, let us say if I mark time of the day, right, and this is say power, and let us say how are we utilizing it. So, let me say this is 6 a.m. Okay. So, this is 12 noon, this is 6 p.m. So, this is 12 p.m. and this is little further down a.m. So, if you do this, you will find that usually in most houses, if they are let us assume that on average everybody is up around 6 o'clock. So, your power usage is kind of high. So, this stays high because lot of things are on, your kitchen is on, your fan is on, maybe grinder is on, many things might be on. So, this is kind of high, everybody is getting ready to go to school or office, and then everybody leaves for school, office, whatever, and then suddenly there is a huge drop in power consumption. So, it will stay low, kind of stay low, maybe at lunchtime it goes up a little bit, then stays low, then comes back, then again sometime in the evening everybody comes home. So, everybody comes home, and then you are back, you are entertaining yourself watching TV or cooking something else, heating some food up, lot of things you do. So, your power consumption goes up and then stays up. So, let us say this is about, so this is around here. So, half a mark would be 9 p.m. So, little past 9 p.m. again everybody goes off to bed, and then it power decreases. So, you just have some basic fan running and then it stays low, and that is how you get 12 a.m. and then if you continue this till 6 a.m. which is the 24-hour mark. So, it will sort of stay low relatively speaking, some basic thing will be going on, maybe a few fans may be running, etc. All your lights will be off, even if you are running AC, you will not be running it in several rooms, you will be running it in a bit. So, you can see this is the profile of power requirement as the day progresses. In most households this is kind of likely to be the case, and 6 a.m. again, as I said, this will start climbing back up to where you saw out here, right. So, this is what you have. Now, if you look at the power generation, okay, so let us say it is solar panel. So, if it is solar panel, then you will have some fairly, let us say from 6 a.m. the power goes up, then by 12 p.m. I am just drawing some schematic. So, let us say this is how the power stays, and then this continues, you have bright sunlight till about 6 p.m. then it starts dropping in intensity, by 9 p.m. you have nothing, and then it drops to 0 and then stays 0, then by 6 a.m. it starts climbing back up when the sunlight starts coming. Okay, so, this is not very accurately done. So, this is solar energy, and this is your household demand. And let us say this is wind power. So, wind power even does not even have a particular pattern. I mean, through the day and through the night you may have all sorts of variation in power. So, just to give you some, I mean, I am just drawing a schematic which has no no basis, I am just accept that to show you that it is kind of random. So, you may have actually fairly good wind power being generated, and then it might just drop down, and then it may just go up, and may go up even higher, it may do this. So, some random thing it might do, and then it will do something like that. So, there is no you cannot very accurately predict what wind power is going to do. So, this is how the wind power is going. So, you can clearly see that if you look at what your house, ultimately let us say you are only powering your house, right. So, let us say you have set up a small plant, either a windmill or a solar panel plant, which powers your house, and say neighboring some 4 or 5 houses are being powered by this. So, the demand for the house is essentially whatever is the red curve that you see here, and clearly the red curve does not match either the green curve or the blue curve. So, it just totally does not match, I mean there is no comparison, they are totally off. So, therefore, you need something to balance this out, right. So, when you need power, if you are just directly connected to it, when you need power at 6 a.m. the solar energy is just barely started producing power, you are asking like 3 times the power. So, you are this is what it is generating, this is what you are asking. So, solar energy is not going to do it for you. So, at some other point in time it is delivering much higher power, and you are demanding much lower power. So, then what is it going to do with that excess power? So, all that is getting wasted. So, therefore, you need something in the middle that keeps collecting up this energy that is being generated, and then makes it available to you when you need it based on your usage pattern, so that you do not feel any difference. In the house you are just going to come and switch on lights and switch on fans and tube lights and LED lights, watch your TV, etc. You do not want that to be disrupted based on what the solar panel is seeing out there, right. So, that therefore, it is in this context that the batteries make a big difference. So, an energy storage device like a battery makes a huge difference, because it helps you manage the supply variation with the demand variation, it evens it out for you. Okay, so, that is why we are looking at batteries, and we will look today at the basic ideas associated with how batteries function, what are the important parts, etc. So, our learning objectives for this class are to state the various parts of the battery and their functions. So, to look at that, what are the parts of the battery, critical important parts of the battery, and what are the functions, to indicate the use of the electrochemical series. So, what is that electrochemical series? I am sure you have heard about it. So, as a part of our complete package of the understanding of batteries, we will briefly visit this electrochemical series and at least highlight the important aspects associated with it, and to distinguish between primary batteries and secondary batteries. So, these are two kinds of batteries that are commonly there, and we will distinguish between them. And also in the context of this discussion, we will also look at the meaning of some terms used in the context of battery technology. In fact, in the few classes that we will deal with this technology, some more terms will be there. I am not introducing all the terms here, because I do not want them to be known completely in isolation. When you listen to the term in the context of its usage, you will better understand what it is that we are referring to. So, these are our learning objectives, parts and functions of the battery, use of the electrochemical series, distinguishing between primary and secondary batteries, and some of the terms that are used in this context. So, this is what we are going to look at. So, what is a battery? A battery first of all is an electrochemical device. It is an electrochemical device. So, what do we mean by an electrochemical device? So, an electrochemical device of course, I mean as suggested by the name, supports an electrochemical reaction. So, it supports an electrochemical reaction. So, for that the parts and whatever the process that is involved is that there is something called an electrode phase, there is an electrolyte phase. So, there are two things in the electrode in the electrochemical device or in a battery. One is referred to as the electrode and the other is called the electrolyte, and the phase simply refers to the fact that it is an physically distinct, mechanically separable, chemically homogeneous part of the system. So, that is basically what we are looking at, and across that, I mean it is a region in that system where the properties are uniformly constant. So, if you take a piece of metal, that would be a phase. Inside that also you may have multiple phases, but generally let us say we have got a pure metal that we have got, we have not got an alloy, you got a pure metal, then you have and it is all in one crystal structure, then it is one phase. Then you have a liquid, that is another phase. You take another piece of metal, that is a different phase. So, that is how you would look at it. So, there is an electrode phase, normally we think of it as a solid, and there is an electrolyte phase, normally we think of it as liquid, but these can change, but this is the normal perception that we have. And importantly, the reaction should occur in a manner that there is a transfer of charge between the electrode phase and the electrolyte phase. So, when that happens, so let me say that this is an electrode and it is sitting in contact with an electrolyte. Okay. So, and then it goes off to some external circuit, some wire is there, let us say. So, now when this electrode is in contact with this electrolyte, you should have a transfer of charge. So, let me just change the color here. So, you should have a transfer of charge this way or this way. Some charge should come from the electrolyte to the electrode or from the electrode to the electrolyte. Some one of the two should happen. If you have this happening as part of the reaction, then this transfer of charge between the electrode phase and the electrolyte phase is what creates this situation that this reaction gets referred to as an electrochemical reaction. Okay, it is an electrochemical reaction, and that is a transfer of charge between the electrode phase and the electrolyte phase. So, that is the point, and the battery device itself that we use is an energy storage device. So, I will highlight this aspect a little more couple of slides down the through this class, little later in this class, but that is just something that you need to keep in mind. So, a battery is an electrochemical device and it also happens to be an electrochemical storage device. So, these are two characteristics of a battery, that it is an electrochemical device. So, there are the reactions occurring there are electrochemical reactions, and it happens to be an energy storage device. So, what are the major parts? As I mentioned, there should be an electrode and an electrolyte, but for the battery to be complete you actually need two electrodes and an electrolyte. Okay. So, one electrode we refer to as the anode and the other electrode we refer to as the cathode, and in the middle there is the electrolyte. Okay. So, that is what we have. So, the electrochemical reaction, so there are actually two electrochemical reactions that are happening. There is one reaction that is happening in this region between the anode and the electrolyte. There is another electrochemical reaction that is happening between the cathode and the electrolyte. So, in each interface, the cathode electrolyte interface, which is this region here, this is a border between these two. So, this region here in this border as well as in this border. Let us assume these are electrodes are plain electrodes, flat electrodes, flat metallics electrodes or whatever. So, in these two borders there is a reaction that is occurring. So, there is an electrochemical reaction that is occurring between the cathode and the electrolyte. There is a different electrochemical reaction that is happening between the anode and the electrolyte, and these two reactions are allowed to interact with each other using two different pathways. One is the electrolyte, that is one pathway, and the other is the external circuit, that is the other pathway. Okay. So, that is the other pathway. So, The external circuit could be anything. I mean, you could have, maybe you have a bulb there or a fan there or whatever, or you just have some measuring device that measures what is going on. But basically this is what it is. So, there are two pathways through which these two reactions are interacting with each other. One is the external circuit, one is the electrolyte. And the way this system works is that through the electrolytes there is movement of ions, okay, movement of ions. So, ions are moving through the electrolyte, and in the external circuit you have movement of electrons. So, that is what we have. In the external circuit there are electrons moving, in the electrolyte there is ions moving. And so, if you look in terms of property, what is property is being expected of these various parts, especially with respect to the electrolyte. The major property that is required is that the ions should be able to move quickly. Okay. So, the electrolyte should have good ionic conductivity. And that simply implies that the ions can move quickly from one side to the other side, whichever side they are moving. They may be moving from cathode to anode or anode to cathode depending on the reaction, but whichever way they are moving they should be able to move quickly. If they move slowly, that is slowing down the overall reaction, and that impacts the current coming out of this reaction. Okay. So, this has to have good ionic conductivity. Importantly, it should have poor electronic conductivity. So, it should have good ionic conductivity and poor electronic conductivity. Why should it have poor electronic conductivity? This is only for the electrolyte that I am talking about. So, this is for the electrolyte. Okay. So, for the electrolyte it should have good ionic conductivity and poor electronic conductivity. So, why should it have poor electronic conductivity? It needs to have poor electronic conductivity because we want these electrons to go through the external circuit, only then it does some work for you, right. So, if you have a bulb which is sitting in the external circuit, that bulb is lit up, that LED or whatever that you have put in the external circuit is lit up only if electrons pass through it. Now, if you, on the other hand, if you gave some some internal path for the electrons to pass, then the electrons will not come to the LED, they will actually go in within the cell itself, and that is a waste of the reaction. So, this reaction on the anode and the reaction on the cathode are generating these electrons. These electrons you want in the external circuit, only then something happens. And so, if you accidentally provide an internal path for the electrons to go, then you have lost those electrons, or if 10-20% of the electrons go that way or 50% of the electrons go that way, half the current that you have generated has been wasted. And therefore, the electrolyte should have this twin property of having good ionic conductivity and poor electronic conductivity. This combination is very important. It should actually be from the perspective of electron movement, it should be an insulator, it should not be a conductor of electrons. Okay. So, that forces the electrons to go through the external circuit, and that is how we end up using the battery. So, that is the idea here. Now, we mentioned these terms anode and cathode, and as I said, maybe many of this at differing levels of detail. You may have even seen it in high school days and some part of your college days. I would still like to highlight some specific points associated with it, because I think often people have confusion on these points, and therefore I will highlight some points, and then that makes our discussion more complete and cogent. So, we will do that. So, we use these terms anode and cathode. Now, lot of people then associate it with something like negative electrode, positive electrode. They get lot of these terms are used, and sometimes it is confusing. Now, the way you need to understand it is that there is only one strong definition of what is an anode and what is a cathode, and then once you understand that definition, everything else is related to that definition. So, the definition is that anode is the electrode where oxidation is occurring. Okay. So, anode is the electrode where oxidation is occurring, and oxidation means loss of electrons. Anode is the electrode where oxidation is occurring. If oxidation occurs, there is a loss of electrons. Cathode is the electrode where the opposite is happening, which is reduction, and reduction means gain of electrons. So, what is gaining electrons? Some species is gaining electrons, some species is gaining electrons, what is losing electrons? Some other species is losing electrons. Okay, so that is the way you have to think about it. So anode oxidation, cathode reduction, that is really the main definition. So you can look at any electrochemical circuit and try to understand where oxidation is happening, where reduction is happening. Wherever oxidation is happening, that is the anode, wherever reduction is happening, that is the cathode. You can even have electrochemical cells where on the same metal, one region of the metal is undergoing oxidation, another region of the same metal is undergoing reduction. So that location where the anode oxidation is happening, that location is called the anode, the other location where reduction is happening is called the cathode. And so you may even have like 10 such locations, you may have 10 locations where reduction is happening, 10 other locations where or say 7 locations where oxidation is happening, but at a higher rate. Then those 7 locations are anodes, these 10 locations are cathodes. So that is the way you should remember it. So now if you look at this definition, anode oxidation loss of electrons, and you go back to this figure. So at the anode we have oxidation occurring at this anode, and then there is a loss of electrons. So what is happening? Those electrons are the ones that are coming out into your external circuit. So whatever material is there in the anode is undergoing that oxidation, and because of that oxidation electrons have been released, and they are not in a position to go through the electrolyte because the electrolyte does not have electronic conductivity, and they are forced to go through the external circuit. So that is why when you are using the battery, when you are actually using the battery, the location from which the electrons are coming out is the anode. Okay. And as you continue using the battery, the cathode is the place where reduction is happening, there is a gain of electrons. The only place where it can gain electrons from is the external circuit, because that is where the electrons are coming. So that is how these electrons are going in here. So reduction is happening here. And this is where oxidation is happening. Okay, so oxidation is happening at the anode, reduction is happening at the cathode. So now you understand the terminology. So anytime you are confused, you try to figure out where the oxidation is happening, where the reduction is happening. I will touch upon this once more in another context, and then I think it will become really clear to you. So at that point, so you do not have to just memorize that zinc is the anode, say silver is the cathode. You do not have to memorize like that. In that cell you figure out where the oxidation and reduction is happening. Importantly, you have to understand that those circumstances can change. We can make what one electrode is when one electrode is undergoing oxidation, you can create other circumstances where that same electrode now undergoes reduction. Okay. So during the time that it was undergoing oxidation, it was behaving like an anode. During the time that it is undergoing reduction, it is behaving like a cathode. So that is the point you have to remember. That is why this definition is important, because the exact same metal in the exact same solution can be forced to do one reaction in preference to the other reaction. When it is forced to do one reaction in preference to the other reaction, based on the reaction that is happening, you decide whether it is anode or cathode. Okay, so that is the point. So now the electrochemical cell, what we do as we saw here is that you have this anode and cathode, and so you can have a whole bunch of anodes and cathodes. So you want to create a situation where you understand what will happen when you take one anode and put it in or one material and connect it to another material with some electrolyte in the middle. You want to understand what will happen, right. So to do that, we have to try and create some standard versions of these combinations, and once you understand how the standard versions behave, you can couple two standard versions, and then from that you will know what that combination will do, and then from there you can create a non-standard version of the same combination. So that is the process by which the people understand what a battery does, right. So you have to first come up with a standard version for an electrode and an electrolyte, and like that you will have several such standard versions. Then you pair them up, so then you have one electrode, one electrolyte, and then the electrolyte and the second electrode, so that becomes a complete pair. Again, they are still under some standard conditions, so there is some behavior associated with that, and then you may use them in non-standard conditions, but how it will behave in non-standard condition is something that you learn from how it behaves in the standard condition. So this is how you do. So what we basically do is that the electrochemical cell will typically consist of two electrodes. So let me just put some kind of a beaker here, and there is some electrolyte here, and some membrane which may be a slight separator which does not allow complete mixing of the two electrolytes, because you may have a slightly different electrolyte on one side and different electrolyte on the other side. You put one metal in here and another metal here, okay, and the let us say this is metal A and this is metal B. Okay, so, A and B you have. So, what we will have is you will have the possibility of this reaction here, that is A going to A plus E minus, and similarly here you will have the possibility of the reaction B going to B plus E minus, and these could happen reversibly. Let us assume that they are happening reversibly. So, in other words it can do both ways. Okay. So, this is likely happening, and then let us connect this in an external circuit, and here we will put a voltmeter and we will connect it up this way. Okay. So, what we are doing is we will also say that the electrolyte that is here contains 1 molar concentration of B plus ions, and the electrolyte here contains 1 molar concentration of A plus ions. So, this combination that you have here of a metal A sitting in contact with a solution that has 1 molar concentration of its ions under 1 atmosphere pressure and let 25 degrees centigrade, this combination is referred to as a standard electrode. So, this is a standard electrode. Similarly, here also you have a standard electrode. When you combine two standard electrodes like this, and that is why you have this membrane in the middle, because you have A plus ions on the left side and B plus ions on the right side, and so you do not want a massive mixing of them, you want to maintain the standard condition, that is how it is done this way. Then you measure a voltage. This voltage is the voltage between two standard electrodes, okay, and this is consistent with the voltage difference that you will measure between these two electrodes using the standard electrochemical series, which we are going to see in just a moment. Okay. So, you have various possibilities for metal A, you have various possibilities for metal B, you can keep on taking different combinations and you can measure these voltages, and typically this voltage is the difference in voltage between these two electrodes. So, now you have wide range of different voltages. So, it gets confusing. So, you will have all sorts of different combinations of different pairs of materials you can take, and you will have, I mean, infinite possibilities you may have of these potentials. So, what we do instead is we try to standardize one part of the cell and then compare all electrodes with respect to that standard part. So, what is that standard part? It is simply an electrode which contains a beaker. So, let me just change that here. So, you will now have some, let us say some beaker of this sort with one small opening this side, in which we will put actually the electrolyte here will be 1 molar of H plus ions. Okay, 1 molar of it is an acidic electrolyte. So, some acid is there, but with 1 molar concentration, and in this you bubble hydrogen gas, H2 gas is bubbled. So, that bubbles up. Okay, so, at 1 atmosphere pressure you are bubbling this gas and it is bubbling up, and in this you dip a piece of platinum. Wire, and from this you can connect it to some external circuit. Okay. So, if you do this, then you create this reaction of H2 going to 2H plus 2E minus. That is the reaction that is occurring in this electrode. This is referred to as the standard hydrogen electrode. This setup that you see here is the standard hydrogen electrode. Or SHE for short, it will be called SHE, standard hydrogen electrode, SHE. So, this now becomes a standard So, in the pair that you are seeing on the left hand side of your screen, in that pair you can always remove, let us say B, instead of B you put this electrode SHE, instead of B you make put SHE, then you will get the standard potential for A. So, A versus this A part of this cell, this standard electrode with A as the metal, if you combine it with SHE, you will get its standard electrochemical potential. Similarly, you combine B separately with SHE, you will get its standard electrochemical potential. So, like this you can get instead of simply coupling A with B, you couple A with SHE, you couple B with SHE, you couple C with SHE, like this you get potentials always with respect to SHE. And then once you get the potentials with respect to SHE, you can get the potential of A versus B by simply adding those potentials or subtracting those potentials based on the way in which your reaction is being written. So, if it is written always as a reduction potential, you subtract those potentials. So, by making these combinations of A versus standard, I mean this A half of the cell versus the standard hydrogen electrode, B half of the cell versus standard hydrogen electrode, etc. By doing this and noting down those potentials, we create this standard electrode standard electrochemical series. Okay. And in this case that SHE is sitting here, the SHE potential is arbitrarily set as 0. So, this is an arbitrary choice, it is set at 0, and with respect to that we note down all the potentials. So, you combine gold with silver, I am sorry, gold with hydrogen, and you got that potential. You can combine silver with hydrogen, you will get this potential of plus 0.8 volts, and then similarly you can combine say zinc with that hydrogen electrode, then you will get minus 0.763 volts. So, like this you can combine different electrodes and get those respective potentials. So, now if you wanted to combine silver with zinc, you simply do 0.8 minus 0.763, and you will get a cell potential of 1.563. So, that is the cell potential of these two. So, that is how you use this standard electrochemical series by looking at all of these potentials as independent potentials and then subtracting them. Point to notice, the hydrogen electrode has been arbitrarily set at 0. So, there is no specific reason why we should be using that as 0, it is just arbitrarily set at 0. And with respect to the hydrogen electrode, whatever is above it is considered to be more what shall I say, more noble or more stable kind of electrodes, and these are more active. Okay, so, more active. So, if you based on how you couple them, more or less whatever is more active means they will tend to get oxidized more easily. So, you tend to the species that are below hydrogen that are towards the lower part of the standard electrochemical series are all going to try and behave like anodes, and those that are noble which are on top of the electrochemical series are trying to most likely going to behave as cathodes. So, any pair you take in this standard electrochemical series, you look and see which one is above, which one is below on this electrochemical series. The more positive one behaves as a cathode, the more negative one behaves as the anode in this electrochemical series. Please also note these are all written as reduction reactions. Okay. They are all written in the reduction reaction. So, in that mode this is the potential. If you reverse the reaction, the potential will get become negative. So, whenever you do so that is why I got 0.8. So, what I have basically done is I have written Ag plus E minus will give you Ag, and then let us say let me combine it with let us say lithium, for example lithium. So, lithium plus E minus gives you lithium. So, if I subtract these two, so this potential is 0.8. So, this is 0.8 and this is minus 3.4, right. So, if I subtract these two, then I will have Ag plus Li gives you Ag plus Li plus, if I subtract these two reactions, and then the potential is simply 0.8 minus of minus 3.4, and therefore you will get what is it 4.2 volts. and that is because the second reaction now happens in reverse, and that is basically so, because one has to get oxidized, one has to get reduced, and whatever is above has a tendency to get reduced. So, this is how we get the standard potential for this cell. So, any combination we get, we try to find out the standard potentials required. So, every battery will have something in the anode, something at the cathode, and you can know under standard conditions you can figure out what is the difference in potential. Now, this is I must also point out that we keep referring to the standard condition. So, you have to always please remember that this is only under standard conditions. Okay, so, and the standard condition is this metal sitting in 1 molar concentration of its ions. So, that is the standard condition, but you can actually do this under non-standard conditions also. And in fact, so therefore, that is why when you make a battery and you measure its open circuit voltage, that may not necessarily match what you will see in the from the standard electrochemical series. And the specific reason why that is the case is that the two materials that you have selected there may not be sitting in their standard conditions. So, if you change the condition, then you can use this standard condition as a starting point and figure out what its potential will be in the non-standard condition, and then that is the potential you will use for doing this kind of calculation that we just did here. Okay, so the calculation that I just did here assumes standard conditions. It assumes that the two electrodes are sitting in standard conditions. If they are not sitting in standard condition, under the non-standard condition you should find out what would this potential have been and what would this potential have been under the non-standard conditions, but the process would be the same. You get those two potentials under the non-standard condition and you do the subtraction, you will get some answer. And in fact, if you go to non-standard conditions, you can even create a situation where what material is showing up as an anode in the showing up as being more active in the standard electrochemical series will now become more noble, and therefore, you may even get a potential that is negative. If it shows you a potential that is negative, it simply means that the reverse reaction is the spontaneous reaction. The way this is set up, the positive potential shows you the direction in which the reaction is spontaneous. So, right now if you do this combination, silver will keep getting reduced, lithium will keep getting oxidized. That is a spontaneous direction of the reaction, and that is why we got a potential that is positive. Okay, so that is how we use the standard electrochemical series. Okay, so in the context of batteries, a few specific terms. I told you earlier that we have the battery is an energy storage device, and so what is the significance of it? It means that the fuel and the oxidant are stored within the device. So, the significance of this is that the size of the battery is some indication of how much chemical is there in the battery, and therefore, how long it can operate. So, for example, you go to the shop and you buy some same brand battery, you can buy what we call the Pentorch battery, or you can buy the AAA battery which is even thinner than that, or you can buy D cell or C cell which are bigger batteries. So, for the same brand, same kind of chemistry that is there, the thinner battery will last lesser time, the thicker battery will last longer time if you use it to power the same device. So, let us say you connect the thinner battery to power a LED, that LED let us say will run for 10 days. If you connect it to a thicker battery which is twice that volume, I am assuming if it is twice that volume, instead of 10 days it will now run for 20 days. So, the size of the battery decides how long it can operate. In energy other kind of device which is the energy conversion device, the chemicals are stored outside of the device, they are not stored in the device. So, later when we look at fuel cells, that would be an energy conversion device, and the chemical being stored outside or being stored inside may not seem like much of a difference, but operationally it is a big difference, because it means that the size of the device does not decide how long it will last. So, even with a small device you can have it running for an indefinite period of time, because you are just supplying the chemicals from outside, and that is why those devices are interesting and are more flexible. And in fact, a device that you are used to very commonly, which you have not thought of in this in the context of this terminology, is the internal combustion engine. So, your internal combustion engine, or ICE, internal combustion engine, which is what is the engine that is there in say your moped or your motorcycle or car, whatever. No? So, there the petrol is sitting in the petrol tank. So, the size of the engine, if you say I have a 1.2 liter engine, that does not tell you how long that engine will run. That how long the engine will run or how long the car will run, it depends on the size of your petrol tank, how much petrol you have got in the petrol tank. So, you fill your petrol and it will last for the duration of that petrol tank, and as it gets close to empty, you simply refill the petrol and you can keep going. So, that is the convenience of an energy conversion device. You simply have to tank up, change the tank and keep going, whereas in an energy storage device like a battery, you have to do recharging, okay, because that chemicals have to be now corrected in some form, or in other words reversed in some form within that device, and that takes time. So, that is the difference. Okay. Also in this context we have this idea of a cell and a battery. So this is something we should at least be aware of. I mean, we may still use it in commonplace terminology, and that is how I even used it in earlier part of this class, but strictly speaking what we refer to as a battery, and we say, we tell somebody in our house saying, hey, go to the shop and buy some battery and come, right. That actually at that point we are asking them to go and buy a cell, we are not asking them to go buy a battery. A battery is actually a collection of cells in series or parallel. So if you take your let us say television remote and you open it, right. So inside that you will have two batteries, right. Actually what you have are two cells, and they may be sometimes pointing in the same direction, in which means that they are two cells sitting in parallel, or we may have them inverted, one pointed in this way and the other pointed the other way, in which case they are in series. So two cells there are sitting in either series or parallel based on how the remote has been designed, then that combination is called a battery. So similarly even a remote control toy, in the toy you will have some few cells, in your remote you will have a few cells, you will find in some case it is sitting in series, some case it is sitting in parallel. This combination is called a battery. Strictly speaking that is the terminology that is used, and each one of them individually is called a cell. So that is how the terminology is used, but we of course in common usage we tend to simply call it a battery. So at least we should be aware of this definition, we may not use it very strictly, but if you ever run into the word cell and you run into the word battery, you should know the difference. So this is the idea. Okay. Also in this context we have something called a primary cell and something called a secondary cell. These are the terms that are used in a more technical sense, primary cell versus secondary cell. A primary cell is basically a single use power source. So these are the kinds of cells that cannot be recharged. In other words, the chemicals that have been used in that, the chemistry that is being used in that cell is such that it is not reversible. It is not reversible chemistry. So once the reaction is complete, you cannot simply flow current in the opposite direction and get those reactions to go back to their previous condition, the reactants to go back to their previous condition, or to make the products go back to being the reactants. So that is not possible with that. So we have lot of those cells that we buy in the shop which are single use cell. So you use it in your remote, once it is done you throw it away, you go buy a new cell, right. So we do not necessarily keep recharging that. So that kind of a cell is referred to as a primary cell. That is the correct technical term for it. Similarly, the opposite is true for what is a secondary cell. These are the cells that we in common usage refer to as rechargeable batteries. That we say rechargeable battery, that term that we use is the term that is being used for this technically indicated item as a secondary cell. What is being indicated technically as a secondary cell, that is what we are referring to as a rechargeable battery. So these are cells where if you reverse the direction of current, you will have the opposite reactions happening, or the reactions will happen in opposite direction, and you will get back the original reactants that you started with, and that is a secondary cell. And therefore this and so you should keep that also in mind, that not every cell is reversible. So that is why you see those warnings in those rechargeable units saying you cannot just put any cell that you want in there, only that specific cell you have to put in there and recharge, because there is also something associated with the voltage. First of all, some cells cannot be reversed, so if you send force current through them, they may just explode or something bad may happen. So you do not want that happening. Only some cells can be recharged, so only they should be recharged, and even there you should only put it in the specific recharger, and not just you cannot take different brands and just throw them into different rechargers, because the recharging unit is designed to work correctly with this chemistry, work correctly with that voltage associated with that chemistry, and so you should not arbitrarily mix them. So this is the difference. So now there is another aspect of this battery technology that we should be aware of. The voltage that we measured, the standard electrochemical potentials that we measured, the potential of that combination, that pair that you then subtract one potential from the other and you get the voltage of the cell, etc., right. That is the thermodynamics of the cell, that refers to the thermodynamics of the cell. So that is the theoretical condition which represents the driving force for the cell to operate. It represents the possibility of the reaction to occur, the drive for the reaction to occur, etc. When we draw current from the cell, that represents the rate at which the reaction is happening. That is called, so the thermodynamics gives us cell voltage. Okay, so thermodynamics, which represents the ability of that reaction to happen, gives us the cell voltage. When and so that ability is something that we typically measure in open circuit conditions. So you just put a voltmeter across your cell and you measure a voltage. That cell voltage represents the thermodynamics of that system and represents the ability of that cell to perform. On the other hand, when you draw current from it, that represents the kinetics of the system, that represents how fast that reaction will happen, okay, and that is the cell current. So, cell current is the kinetics, cell voltage is the thermodynamics. So, these are two very important parameters, we often do not realize it, but these are the two that decide many things in our in nature. In nature many things are decided by thermodynamics and kinetics. So, for example, if you take a piece of wood, right, you take a piece of wood and you light a fire, the wood burns. So, in other, why does that happen? Because the wood has a tendency to burn. What is happening when wood burns? Wood burns and then all the carbon in the wood becomes carbon dioxide, right. So, and the fact that it is burning or continuing to burn means the carbon prefers to become carbon dioxide. So, carbon dioxide is the more stable condition. So, if you allow carbon to react with oxygen, it will react with oxygen and form carbon dioxide. Okay. So, this ability of carbon to react with oxygen and form carbon dioxide, and this tendency of carbon, this tendency of carbon to react with oxygen and form carbon dioxide is represented by its thermodynamics. That tendency is captured by thermodynamics. So, that is why you get delta G for that reaction, the delta G for that reaction would be negative. That means it is spontaneously, it has a direction in which it will tend to go, the C will react with O2 and form CO2. Okay. So, there is a driving force for that reaction. Okay. So, it is trying to happen, but it is also important to understand that when I keep a piece of wood in air, I just keep it on the table or even the table itself is wood, why does it not immediately burn? Now, there is a tendency that you understand that carbon dioxide, it would rather be carbon dioxide than carbon. Why does it just not burn? You just keep it there, it does not just spontaneously burn and disappear into carbon dioxide. It does not, because you have a driving, you have an activation energy barrier. There is an activation energy barrier. So, that is how, so you will have the reactant in some level, you will have the product at this level, and so this is the energy difference, this is energy, and therefore, since you have this drop in energy when you go from C to O2 from C to CO2, that is a desired state of affairs, but to go to this distance you have to actually go past a activation energy barrier, and it is this activation energy barrier that is what makes the world stable the way we see it. So, that is why the clothes we wear, the things that we use, etc., are not just spontaneously catching fire and getting oxidized, even though the oxide will be the more stable state in which it will be there. So, there is an activation energy barrier which prevents a reaction from happening, even though thermodynamically the reaction is trying to happen. So, in the context of things we have to understand the kinetics, the rate at which the reaction is happening is an important aspect, and so and that rate is often affected by the activation energy barrier. So, the activation energy barrier decides how easy or difficult it is for the same reaction to occur. You make the activation energy barrier smaller, the reaction will happen faster, okay, and that is what the catalyst does. Whenever you use a catalyst, that is what it is doing, it is reducing the activation energy barrier, therefore making it easier for the reaction to happen, but the ability of the reaction to happen is the same. So, this point here and this point here are not changed, only the barrier is changed. So, you may have a smaller barrier or a larger barrier, and that, so if you want, so for example corrosion is something, is an undesirable reaction. So, we do things to increase the barrier for corrosion. So, we are increasing the activation energy barrier for the corrosion. On the other hand, so if you are talking of a corrosion reaction, you are basically trying to do this, you are trying to increase the barrier. If you are on the other hand, you are talking of some battery kind of situation where you want the reaction to occur fast, you are trying to do this, trying to reduce the activation energy barrier. So, that is what you are trying to do with respect to the activation energy barrier. So, this is the point. So, there is thermodynamics and there is kinetics, and it is a combination of these two that you see eventually as the performance of your cell in terms of voltage and current respectively. And the cell characteristics are captured by a few different terms. We typically only look at voltage. So, we typically keep referring to the voltage in the cell. So, this is the point that we keep referring to, that is the open circuit voltage. The current is what we draw from the cell, the rate at which the reaction is occurring, the rate at which those electrons are being drawn, and so the combination of those two gives you the power in watts. So, that is simply V into I. So, that is the characteristic of the cell. The capacity of the cell is a term that we use, which represents the total charge that is available in the cell, and that charge is typically in coulombs or ampere hours. So, that is basically whatever current you are drawing times the duration for which you draw the current. So, that is where if you have the same chemistry and you have a smaller battery and you have a larger battery, the capacity of the larger battery is more than the capacity of the smaller battery. So, even if you draw the same current, let us say it is twice the size, the duration for which it will last is twice as long. So, even if you are drawing the same current, if one battery lasts 1 hour, the thinner battery lasts 1 hour, if the thicker battery is twice its size, let us say, the thicker battery will last 2 hours. So, for the same purpose. So, if you are lighting some product, some place and you want light to be on for 2 hours, you should use the thicker battery and you do not want to change the battery, right. So, the time comes in there. So, the time is associated with this process in this manner and that is how we get it. And the energy that is available is power into time. So, current into time gives you the capacity, power into time gives you the energy that is available, and that is in joules or watt hours. Okay. So, this is how we get the different parameters that we use to understand what is possible. So, the power, the energy that is available also includes the fact that it has it is not just the current that is coming out, but current is coming out at some voltage. That is why you have so you have V into I into time. This is energy, and of which this is power, right. So, V into I into time. So, the energy equals V into I into time, the capacity equals I into time. Okay. So, that is the capacity. How long will it last? This is what is the total energy that is available. So, this is the this is amperes and that is hours. So, ampere hour you will get, this is watts and that is hours. So, watt hours you will get. So, this is the different parameters here. Okay. So, in conclusion, so we have just now briefly looked at all the basic ideas associated with the battery. So, our main conclusions here are that batteries have specific parts that can have dramatically opposite functions, and that is what I meant. What I mean here is the idea that you have an electrode phase and you have an electrolyte phase, and what we are demanding of the electrolyte phase in terms of conductivity is the opposite of what we are demanding from the electrode in terms of conductivity. Electrode should have good electronic conductivity, electrolyte should have good ionic conductivity, and they should be in opposition to each other. But as a reaction they will all assist each other. So, that is the point. The electrochemical series is the starting point to understand battery voltages, but as I pointed out, the electrochemical series is under standard conditions. So, this is standard conditions, always please remember that these are standard conditions, but that is the correct place for you to start, because otherwise it is confusing. There is just no end to all the conditions you can set these various materials to. So, we set some standard conditions, and that is this standard electrochemical series, which is the place where we look at the standard electrode potentials, which means the electrodes are set under some standard conditions. Any non-standard condition can be derived from starting from the standard condition, and that is why it is a nice process. And there you subtract one electrode from the other electrode, you will get the open circuit potential, and then you can decide which way the reaction is happening, and that potential itself may change. So, you have from the standard electrochemical series you have one that is above, which is noble, one that is below, that is active. So, if you take the difference, then you will find that this is the open circuit potential, and this is the so the what is above is the one that will undergo reduction, what is below is the one that will undergo oxidation. So, this lower electrode is your anode, the upper electrode is your cathode. But if you go to non-standard conditions, this potential can go low or high, this potential can also go high or low. So, supposing this were to go high and that were to go low, because you have gone to non-standard conditions, then what originally, so now you can see that their relative positions have reversed. So, what originally served as the cathode will now become the anode, what originally served as the anode can become the cathode. So, you can see that all these things are possible with respect to the electrochemical combinations that are possible. And I also told you that there are primary and secondary batteries and these are all very commonly available and commonly used. Primary batteries are single use batteries, secondary batteries are rechargeable batteries. So, that is our basics that I felt are relevant for the discussion on batteries. We will look at some battery systems and how batteries performs and so on, and these phenomena will all be relevant in that context. So, that is the discussion and main conclusions for today's class. Thank you.